Okay, it's 11:05 and I think we should get started. All right. So this class, we're going to finally finish the water treatment. Okay, so last class, I think we stopped at the water hardness, and unfortunately, that's going to be a part of our second exam. So I wanted to postpone the deadline for the homework so that you guys can um, better know this topic and do some calculations here. Okay. So again, if we do a recap of our last class. So last class, we mainly talked about the sedimentation basin and the sand filters, right? So for both of these systems, we have a general equation that is basically velocity equal to Q divided by A. Okay, so Q is the flow rate. And then A is the surface area. It's just the V here has different meanings for sedimentation basin and the sand filtration. For example, for the overflow rate, I think this is defined as V0, right? So this overflow rate is basically the critical settling velocity of the particles, right? So that's normally designed by the, or designated by the water treatment facility, right? And then you can, based on the flow rate, you can design what is the area of the sedimentation basin. And for the sand filtration, this V here is called the loading rate. Okay, so it's basically the phase velocity of the water penetrating through the sandbox. Okay, and also this loading rate is going to have a maximum value. And normally during the operation of the water facility, we're going to designate a fixed value as well. So based on the flow rate, we can design what is the area of the sandbox. So here I have a quick quiz question, okay? So it is asking what's going to change if we suddenly decided to change the flow rate of the sedimentation basin, okay? So basically it's saying that a sedimentation basin was designed with a fixed overflow rate. So it was found that the flow rate of the water becomes twice of the original design. So how should we change the surface area of the sedimentation basin? So here are four answers here. And this is going to be the first quiz of our class. Okay, 5 more seconds. Okay, we'll stop here. So most of you guys get the correct answer. All right, so we're using this equation again. So basically, if the flow rate increased by 100%, right? So as it says, it's designed with a fixed overflow rate, which means that this number will not change. So what's going to happen is that we have to increase the area by 100%. Okay, so it is quite straightforward if we know directly know this equation here. So last class, in the end, we talked a little bit about the water hardness, right? So one interesting thing you might already notice is that if we go back to this schematic diagram of the water treatment facility, you see that we covered the coagulation and flocculation in here, right? And then the sedimentation basin and the sand filtration, these are covered here. So the screening is quite straightforward. We're just using a mesh to control basically to remove the larger chunks of pollutants. All right. So one of the things that we have not covered are the chlorination, right? Basically, the chlorination is for disinfection. Right? And the fluoridation, this is for protecting the teeth of the residents, right? And then we didn't cover the pump. So I guess for the pump, you should already know that from the hydrodynamics, right? So what is the power of the pump for you to lift the water to a certain height, right? So if you're interested, you can go over the sections in chapter 10. So there are more descriptions of these processes. So basically, these are the things that we're quite interested in. Okay. So for chlorination, one thing I want to point out is that normally people will put a basically an overdose of the chlorine in the water. Okay, so mainly because we want to make sure that the chlorine can stay basically we can have an extra amount of the chlorine to remove the potentially more pathogens in the water. Okay, so normally the amount that we want to ensure is that the chlorine level has to be larger than 2 milligram per liter. Okay, before they're distributed to the households. So the reason why we want to have this overdose is because the chlorine is not very stable. Okay, so it can get disassociated or get reacted with other species. So while the water is being transported to different locations, the chlorine concentration is going to reduce, right? So it might happen. And so if we don't have this overdose here, so one thing that might happen is that the chlorine concentration, when it reaches to the household, it might drop down to 0. So if it's 0, then it doesn't have any function of disinfection anymore, right? So this is one thing that I want to point out regarding the disinfection. So if you notice in this diagram, basically we don't have any section for dealing with the hardness, right? So when we deal with the hardness of water, so this process is called the softening, water softening. Okay, so you see here in the schematic diagram, we don't have any process that's softening the water. So this makes sense because we're intaking the water from the lake, right, from the surface water. So in the surface water, there are not a lot of rocks or minerals or formations that can dissolve these calcium or magnesium ion into the water. But when we're taking groundwater, for example, in Rolla, we're heavily relying on the well water, groundwater. So if you consider the groundwater, what happens is that it's all packed with rock, right, or minerals, and the water is flowing by from here. So it's going to be more likely that the minerals can get dissolved into the water, and then we can get a higher concentration of these calcium or magnesium ions. All right. So last class, we generally went over the problem of the hardness. So basically, people have to determine what is the hardness of the water before they're distributed to the household. So just imagine if the hardness is too high, then for example, during the summer, then it's very easy to form these solids because they're not stable under higher temperature, right? So it's likely that these hardness can block the water pipes and then cause leaks or cause bursts, right? So they may cause problems. So we have to measure the hardness of the water before we distribute it to the household. And also we need to soften the water if we realize that the hardness is too high. Okay, so the hardness is defined as the summation or the sum of all the polyvalent ions, mainly because these polyvalent ions can form solids, right? If you imagine, let's say calcium bicarbonate, which is soluble in water, right? And when you heat it up, you can form calcium carbonate, right? So the same for magnesium carbonate or the iron carbonate, right? Or the ferrous carbonate. Right? So all of these can form solids. So that's why the hardness is defined as a sum of all the polyvalent cations, right? So for the, like, let's say the monovalent, basically it means that they carry one charge only. For example, the sodium or the potassium, or the ammonium, right? So for these ions, they will not form solids. Basically, they're very stable. They can dissolve in water very easily, right? So we won't form solids like these white scales when we heat it up, right? So because of that, if you imagine how we do this calculation here, we shouldn't directly add up all the mass concentrations, right? Let's say the calcium has a mass concentration of 20 milligram per liter, or the magnesium 20, right? Let's say iron is 1 milligram per liter. So we cannot directly add their mass concentrations, mainly because different iron, they have their own molecular weight, right? So for example, for magnesium, it has a very small molecular weight, which means that they may be more effective to form these scales from these sedimentations. So that's why when we represent the total hardness, we need to show them with the unit of millimole per liter, right? Basically the molarity. We need to divide their concentration, mass concentration by their molecular weight, right? To calculate what is the total hardness. And more commonly in the engineering, what we do is that we'll convert it into an equivalent mass concentration as calcium carbonate. Okay, so last class I briefly went over why we decided to use this mass concentration, or basically to show the equivalent mass concentration of the calcium carbonate. So the reason for doing this is in the water softening, if people want to remove the hardness of the water, what they're going to mainly rely on is the calcium hydroxide. Okay, so these are the reactions that they're going to rely on. So for example, if you want to remove the calcium bicarbonate, which is the major species that's causing the hardness, right? So what's happening is that we're going to put in calcium bicarbonate or the calcium hydroxide, okay, into the water. And then what happens is that these two can react with each other to form two number of the calcium carbonate, right? These are solids. We remove the hardness ions in the water and then form water. So similarly for the magnesium bicarbonate, we can put in the calcium hydroxide and then form the calcium carbonate and magnesium carbonate. So both of them are solids. So this is the way we remove the hardness or the soften the water. So the thing is that this calcium hydroxide actually comes from the calcium oxide when you dissolve it into water. And further, the calcium oxide comes from the limestone calcium carbonate when you bake it, right? When you heat it up at high temperatures, you form calcium oxide, right? And then calcium oxide dissolving water to form calcium hydroxide. So basically, to react with 1 mole of the calcium ion, right? 1 mole of the hardness ion, we need to rely on 1 mole of the calcium carbonate, right? So this is going to be easier if, let's say, a water treatment facility, if they want to purchase the raw material, let's say limestone, okay? So they can directly call the mining company saying that I need this certain amount of limestone. Can you provide that to me? So I'll deal with the rest of the softening process. Okay. So because of this 1-to-1 ratio here, people tend to convert this molarity, or how many moles are there in liquid in water, into the mass concentration of the calcium carbonate. Okay. So here we can do a second quiz here. So I'm asking question why we're using this, we prefer to use this calcium carbonate equivalent concentration, right? So the question is saying that the groundwater has a total molarity of calcium and magnesium ion of 2 millimole per liter. Okay, so how much of the calcium carbonate should be used to soften the water? So if you consider these reactions here. Okay, 5 more seconds. All right, we'll stop here. Okay, so it seems that most of us chose the second answer here. So I will not give you the correct answer. So what I'm going to do is I'm going to set up some breakout rooms, and then you guys can have a quick discussion. Okay, let's say 2-minute discussion, and then we'll come back and then make the choice again. So just remember the question here. I think once I set up the breakout room, maybe the shared screen will be gone. So we have the total molarity of 2 millimole per liter. Okay, so it's asking how much calcium carbonate should be used to soften the water. All right. Okay, so I just created the quiz again. So let's maybe have 10 more seconds to make your final decision. Okay, so I see a tight race here. Okay, so it's either 100 or 200. All right, I'll stop here. Then share the results. Okay, so there are some minor changes. So now I have to say that those who did correctly, you did a good job to convince others. Okay, so it should be 200. So the reason for that is, let's look at this problem again. Okay, so as we mentioned, the calcium ions are reacting with the calcium hydroxide at a 1-to-1 ratio, right? So basically, it's reacting with the calcium carbonate as a 1-to-1 ratio. And then the same for the magnesium. Okay, so reacting with the calcium, or it to continue or to make this reaction happen, we need to have a 1-to-1 ratio of the calcium or magnesium ions with the calcium carbonate, right? So because of that, if you have per liter of the calcium carbonate, right? And then we know that the calcium carbonate has a molecular weight of 100 gram per mole, right? So if you multiply these together, that's going to be 200 milligram per liter as calcium carbonate. Okay, so this is the reasoning behind this. So we need a 1-to-1 ratio between the calcium and magnesium ions. I mean, basically the calcium ion and the calcium carbonate, and magnesium ion and the calcium carbonate. So that's why we can convert it by just multiplying 100 to get what is the required calcium carbonate. It is going to be it is going to be easier if a water management facility knows what is hardness in equivalent of the calcium carbonate. Because let's imagine if we know what is the volume of the tank, let's say that it has a volume of 1 cubic meter. Okay, so 1 cubic meter means that there are, let's say, 200 milligram multiplied by 1,000 liter, milligram per liter multiplied by 1,000 liter. That is basically 200 grams. Okay, so 200 gram is a pretty small amount, but now you know that you can just place in 200 grams of the calcium carbonate. So basically bake it, right, to get calcium oxide, and then further dissolve it into water to remove the hardness, in the water, right? Calcium ion and magnesium ion. So I hope you can understand this better now. I won't give you another quiz to confirm this, but try to understand. I mean, try to understand why we're using calcium carbonate as the equivalent mass concentration for hardness, right? You're going to have a few homework problems and potentially in the exam regarding this question. Okay. So basically, based on the definition, let's say the total hardness is just the summation of all the polyvalent ions, right, in their molarity or as calcium carbonate, right? I'm having this equation here. We can calculate what is the hardness of any water if we know what is the ionic concentrations inside, right? So here it is giving you the chemical composition of a groundwater, okay? So this is a mineral analysis. You see that there are metals, right? You have the iron, you have the sodium, potassium, calcium, magnesium, and barium, right? So to calculate the hardness, we just need to sum all the polyvalent ions, right? So you see that the polyvalent ions are iron here, and then calcium, and then magnesium, okay? So first we need to know what is the molarity, or what is the mole per liter for these ions. So what we can do is, since here is reporting milligram per liter for all of these metals, right? So we need to divide them by the molecular weight, right? Divide this one by 40. This is the calcium's molecular weight. Divide this one by 24, right? And divide this one by 56. This is the molecular weight of the iron, right? And then we need to add them all together, right? So after adding them all together, we will multiply that by 100, right? By 100, that is the molecular weight of the calcium carbonate. Okay, so 100 gram per mole. So with that, you can calculate what is the total hardness, basically in milligram as calcium carbonate. Okay, so here I can just quickly give you the numbers here, which is 67.2 divided by 40, and then you multiply that by 100 plus 40 divided by 24, multiplied by 100, and then 0.2 divided by 56, multiplied by 100. Okay. So if you further pay attention to these numbers here, you see that this number is very small, right? This is iron. And that's why when we calculate the total hardness, we can mostly ignore all the metal or all the other metal except for calcium and magnesium, which are the most common metal in the underground water. Okay, so we can just ignore this one because this is too small. And you can find out that the final answer is 335 milligram per liter as calcium carbonate. Okay, so this is the total hardness of this water sample here, right? So why do we need to know this? If we know this, we can purchase the calcium carbonate limestone, bake it to get calcium hydroxide, and then remove these hardness ions, right? So with this number here, it's going to be easier for us to make this process happen. So there are some more information regarding the softening process. So as we have said, although the total hardness is the sum of all the polyvalent ions, but we found that the calcium and magnesium are going to occupy the most of these hardness species, right? So another way to calculate the total hardness is we can just add these two together and then show them as milligram per liter or millimole per liter. Okay, either molarity or equivalent mass concentration as calcium carbonate. So people further set up the standards of the how hard the water is, right? So if the hardness is between 60 to 120 milligram per liter as calcium carbonate, then it's called moderately hard, right? So if they are in another range here, I don't know what happened here. Okay. Yeah, I got the screen back. So if they're in another range, then we can say that they can be categorized as soft, slightly hard, moderately hard, or very hard. Okay, so we want soft water because this is going to be less damaging to the, let's say, the appliances or the pipes when we distribute the water, right? So further regarding the hardness composition, people divide them into carbonate hardness. Basically, it's the magnesium hydroxide or calcium hydroxide. So the reason why we want to point these carbonate hardness or these bicarbonate ions is that for these species, we can just use temperature. Most of the time, we can raise the temperature to reduce them because these minerals are not stable. So if you raise the temperature even by a few degrees, then some of these species can get converted into calcium carbonate and magnesium carbonate. They can settle down in the water, right? So we can remove them by coagulation or flocculation, right? So this is a carbonate hardness. And there are also non-carbonate hardness, which basically we cannot use this temperature to control, right? For example, the calcium chloride, right? Magnesium chloride, or the calcium nitrate, right? Magnesium nitrate. So for these species, it's going to be difficult for us to control them by the just by using temperature. Okay, so but we can still remove them by using the let's say by introducing the carbonate species. Okay, let's say we can use soda, right? Soda is the sodium carbonate, right? So sodium carbonate can react with the calcium chloride. And then basically we're forming sodium chloride, which is just salt, and then calcium carbonate, right? So this is the non-carbonate hardness. So now you can see that the total hardness can be further divided into carbonate hardness and non-carbonate hardness, right? Because finally it's the summation. It's the summation of all the polyvalent ions, right? So it doesn't matter whether there are, it doesn't matter whether they're shown in the state of bicarbonate ions or they're shown in the state of chloride ions. So that's why people created this bar graph to show what is the relationship between the carbonate hardness, and non-carbonate hardness. Okay, so what happens is that if you analyze the water sample, what you can see is that under some scenarios, let's say there are too many of these hardness ions, right? And at the same time, you don't have a lot of bicarbonate ions. So because the water is neutral, there has to be some anions that couple or that can bonded with these cations. So these can be chloride ions, right? So under this situation, we call the carbonate hardness are basically the concentration of the bicarbonate ions. Okay, so you see it's spanning the area here, right? This is the carbonate hardness. But the total hardness is just the concentration of all ions, right? The total hardness is everything in here, right? And based on this plot, you can see that non-carbonate hardness are basically corresponding to the concentration of the chloride ions, right? So we may also have this scenario where we have too many or too much of these bicarbonate ions. Let's say in this situation, you have, I don't know what is happening here. You have this amount of the bicarbonate ions, okay? But at the same time, the metal concentrations are relatively low. So under this situation, the total hardness is still decided by the concentration of the metal, right? And then the carbonate hardness is going to be the same as the total hardness. It's because we define it as hardness, right? It's finally determined by the metal concentration. So the carbonate hardness is going to be equal to the total hardness under this situation, right? So we can do another quick practice here. So let's say we have a water sample that has certain pH, and then it also has the concentration of these following ions. Okay, so we have the calcium ion has the concentration of 40, and then magnesium ion has a concentration of 10 milligram per liter. And then we have the sodium and the potassium ions. But we know that for the hardness, we don't need to consider these monovalent ions because they're not forming any solids. And on the anion side, you have the bicarbonate ion in here. Okay, so now it's asking us what is the carbonate hardness or what is the total hardness, right? So under this situation, we should use the bar plot. So the bar plot, what happens is that it draws the cation on the top, and then it draws the anion on the bottom. Okay, so the cation, we see that it's mainly composed of the calcium ions and magnesium ions, right? So we should calculate what is their concentration. Of course, we cannot use their mass concentration directly. So we can convert it into the mass concentration as calcium carbonate. So if you remember, how do we do that? So we used 40. So basically, use 40 divided by 40, which is the molecular weight of the calcium. And then we multiply that by 100. Okay, so you can see that this is going to be 100 milligram per liter as calcium carbonate. And then we can do the same for the magnesium. So divide that by 24 and then multiply by 100, right? So you can see that this one is going to be 41.7 milligram per liter as calcium carbonate. Okay, so if we have these two concentrations, we can draw them on this bar plot. Okay, so basically this is going to be our calcium, and this is going to be our magnesium. Okay, so the total is 141.7 milligram per liter as calcium carbonate. All right, so now we need to draw the anions. Okay, so for the anions, we know that here we have the bicarbonate ion. Okay, so we should do the same, divided by the molecular weight of the bicarbonate ion. So for this one, the molecular weight is equal to 1 plus 12 plus 3 multiplied by 16, right? So that is 61 gram per mole. Okay, so we will divide that by 61. And then at the same time, one thing we need to notice is that we mentioned the calcium and the magnesium, they react with calcium carbonate at a 1-to-1 ratio, right? But for the bicarbonate ion, they're not reacting as 1-to-1 ratio, because consider, let's say the bicarbonate ion can only react with one proton ion, right? Well, for the calcium carbonate, it can react with 2 number of the proton ions. So actually, they're going to react as a 2-to-1 ratio. Okay, so every 2 number of the bicarbonate ion is going to correspond with 1 number of the calcium carbonate. So we need to further divide it by 2 and then multiply by 100. Okay, so this 100 again is the molecular weight of the calcium carbonate. So you can find out that this number is actually 90.2. Okay, so we can draw out the bar for the anion, right? So this is going to be 19.2. This is 100. This is 41.7. And then the rest of it is just the chloride ion or the sulfate ion. Okay, so this is our bar chart. All right, so now if I ask you, what is the total hardness? So the total hardness is a summation of all the polyvalent ions, right? So that's just going to be 100 plus 41.7. So that is 141.7 milligram per liter as calcium carbonate. So if I ask you, what is the carbonate hardness? So the carbonate hardness is decided by the bicarbonate ions, right? You remember here. So basically, you're just going to account for the bicarbonate concentration. So the carbonate hardness here is going to be 90.2 milligram per liter as calcium carbonate. All right, and then the non-carbonate hardness is going to be the total hardness minus the carbonate hardness, which is 141.7 minus 90.2, right? You can calculate what is the non-carbonate hardness concentration in this water here. All right, so this is the way to use the bar chart and then to analyze what is the carbonate hardness and what is the total hardness. So the reason why we do that is because once we know which one belongs to which, we can come up with different methods to remove the hardness. We can raise the temperature. We can raise the temperature of the water, or we can put in the lime and soda, right, to basically form sedimentations for these hardness ions. Okay, so I also have a practice problem. Maybe you can go over this after the class. Okay, so what happens if we change this concentration to 10? Okay, so if we change this concentration to 10, then basically that's going to be a quarter of this original concentration, right? So if you make the plot, you're going to see basically 25 coming from the calcium, and then you have 41. We have 41.7 as the magnesium, right? And then you still have the same amount of bicarbonate ions. This is going to be 90.2. Okay, so now the total hardness is going to be different. And similarly for the carbonate hardness, the same. Okay, so basically now the total hardness should be 25 plus 41.7. And the carbonate hardness is going to be equal to the total hardness, because finally it's decided by the polyvalent ions concentration. Okay, so hopefully you can understand this process better. I know that there are quite many definitions here. You will have a few practice problems in your homework problem. All right. So in terms of removing these hardness ions, people normally use the lime soda ash softening, as we introduced earlier. We're going to use the calcium carbonate. Okay, so we are going to bake it to form the calcium oxide and then calcium hydroxide. Okay, so the calcium hydroxide can remove the calcium bicarbonate ions and magnesium bicarbonate ions. So as we introduced earlier, we can form basically these solids into the water so that we can remove these metal ions, right? So we can soften the water. So we can similarly use the lime species to remove the non-carbonate hardness. Okay, so for example, if there are magnesium sulfate, okay, so we can use the calcium hydroxide, and then we can also form the sedimentation, right? Form this solid magnesium hydroxide here. Or we can use soda ash. So the soda is mainly composed of sodium carbonate, right? The sodium carbonate can react with the calcium sulfate and then also to form this solid here. So that's why it's called the lime soda method. And by using the equivalent concentration as calcium carbonate, it's going to make this process much more easier when we try to control the water quality. So we can also use this relatively newer method. It's called the cation exchange softening. So it's using a similar mechanism. So we can use some resin or some organics and bond it with the sodium ions. And then when we introduce them into the water, this resin is going to be bonded more easily with the calcium ions, right? So you can exchange that basically to convert it into the convert it into the sodium ions into the water, while the resin is going to take this calcium ions away. So what happens is that you can introduce these beads here, right? So these beads are going to attach calcium ions. These are the calcium ions. Originally, they are attached with the sodium ions. So further, you get these beads attached with calcium ions, and then you can collect them at the bottom. Okay, so finally, you can regenerate these beads to convert it back into the resin attached with the sodium ions. Okay, so this is a relatively newer technology. I think people are still mainly using the lime soda method to remove the hardness from the water, right? So that's all for the water treatment section. And for our exam 2, we're also going to end here. Okay, so the exam is not cumulative. It's going to cover everything after the hydrology until here. All right. So again, pay more attention to your homework problems. It's going to be quite similar to those problems. All right. And also go over the class notes. You never know, there may be some multiple choice questions that I raised in the class. All right. Yeah, so the exam is the week after next, after the spring break on Monday. Okay, so it's going to take the same format. All right. So I saw that did Clap raise hand? I think someone raised hand, but maybe that person left. Okay, so if no more questions, you guys have a nice spring break, right? Stay safe. And then we're going to get together the week after. All right.
Have a nice day.
Yeah, you too.
So do we not have, we have class, wait, today's our last class, isn't it? It's Wednesday. That's right. I'm sorry, I'm thinking of another class.
Okay.
Thank you.
Yeah, thank you.